I am a representative of real algebraic geometry in this workshop, and I was asked to talk about the problems and ways that real algebraic geometry can contribute to hyperbolic programming and hyperbolic polynomials, and I've picked two aspects. The first part will mostly be about ways to test if a given polynomial is hyperbolic or not, which is related to the second part of determinantal representations, and in particular I'll talk about the Helton-Winikoff theorem that Michel already mentioned yesterday, and the generalized Lex conjecture, and these types of problems. So as a warm-up, so to speak, let's review some of the words that I will use. So we've seen stable polynomials as a related notion, which is for me in this talk luckily the same, but it looks different. So the half-plane property means if you plug in complex numbers into your given polynomial that have positive real part, you'll always get a non-zero number. So there are no roots sort of in the left half of the complex plane. And stable was, you have the same essentially, but you say positive imaginary part, right? So they look almost the same, but you fix different planes, half planes in the complex plane, where you require the same property. And I will be interested in homogeneous polynomials throughout, almost exclusively, and then these two things are the same, because you can pull out an I or a minus I out of your polynomial and just switch real and imaginary part of your argument by doing that. So really these two properties, for me, are luckily the same. And both of them, in this case, of course, then are related to hyperbolicity, as Michel explained yesterday. So hyperbolic means, for me, always that the polynomial is homogeneous, so I made it part of the definition. And there is a direction, E, that is special for this polynomial. Polynomial has to be non-zero at this point. And when you restrict to lines through any point in this fixed direction E, you get a polynomial in one variable that only has real roots. The definition. Now I will hopefully always use this sign convention, but by reflection on the line, you can also change this to plus TE, and the condition stays the same. That just reparametrizes the line. And because it's homogeneous, sometimes some people write also the variable in front of the x instead of the e. That's a projective transformation of the line that also preserves the property that you only have real roots. So this is, what you do is you write t to the d, you pull it out, and then you here have 1 over t. That doesn't change real rootedness because it's a projective transformation. Okay. And a little sneaky, this is really also nothing, but it reduces the number of variables I have to check on the next slides by 1. If you have a hyperbolic polynomial and you want to check, the definition says plug in any x, but of course you're only interested in all of the lines in direction E. So you shouldn't take any x, but you can restrict to a complement of the subspace spanned by E. For example, the orthogonal complement, because that gives you already all of the lines. Right? That's sort of an affine transformation of the line. So this will reduce the number of variables for our tests by 1. It's a very simple observation that is useful. All right. In Cheyenne's talk, let's see. Oh, yeah. We didn't do this exercise yet, I believe, and it's something you should do at some point. A real homogeneous polynomial is stable if and only if it's hyperbolic in every direction in the positive orthant. That result was mentioned, I think, at least twice already this week. It's a relatively simple exercise that's somewhere on this long sheet. I will comment on the length of the sheet in a moment. Okay, we saw this result due to Petter in Cheyenne's talk that characterizes stable polynomials in the case that the polynomial is multi-affine. So the degree of this polynomial in every variable is at most 1. There are no quadratic xi squared or xi cubed or anything like that. And then the theorem says that the polynomial is stable. So now the polynomial is not homogeneous, so I don't use hyperbolic, but I use stable. If and only if these weird polynomials are non-negative for all choices of I and j. This is my notation for the partial derivative of the polynomial with respect to the ith variable. And so I would like to take a moment to explain where these polynomials come from. They seem a bit mysterious, maybe. And that will prove essentially one of the directions of the theorem, which in my opinion is the far easier one, and the other one is more interesting. And the key word, I think there's a debate about the name, but I've seen many people call these things. I'm going to talk about Wronskians, even though the name is taken in differential equations theory and is a different thing. So it's not the matrix that you may know from differential equations, but it is this expression given any two univariate polynomials f and g. So now I'm only talking about the line. I will form this polynomial. So by the chain rule, that's a polynomial, by the quotient rule. And I claim that if these polynomials have distinct roots, and the roots are interlacing with the definition that we had. If you look at the roots along the line, they alternate. First you have a root of, say, f, then a root of g, then a root of f, then a root of g, and so on. They satisfy this property. This polynomial will be a non-negative, or if you change signs, a non-positive function, but it will not change sign along the real line. And that I made an exercise. That's not too hard to see, but it requires some arguing with roots of polynomials and so on, and it's very much related to the barrier function in Nikiel's talk. So this proves convexity of this function, for instance, if you do this exercise. And these polynomials that show up, so let's do this computation, I claim are exactly of this type. So you argue that this is non-negative just along the lines using this lemma. And so let's do the computation. So what you should look at, so we want to produce the polynomial delta I p delta j p minus p times I j. And so I'm going to restrict a polynomial. Call it f, why not? Namely, I want to take the ith derivative of p restricted to the line x minus t in direction ej. So ej is the jth standard basis vector. So I've lied, maybe not. Doesn't matter really, but let's do just this, and g is the derivative of it. So you take the ith derivative of p and you plug in x minus t ej. So these are two polynomials along this line in this variable, and I claim they interlace by Rolle's theorem. Essentially, it's a real-rooted polynomial. This is a directional derivative because it's stable. So this ei is in the hyperbolicity cone. If you take a derivative with respect to a direction in the hyperbolicity cone, you will get an interlacing polynomial. Did Michel do this? I don't recall. I think maybe almost, right? It's in these derivative relaxations in Jim Rennegar's paper. So if you have a hyperbolic polynomial that looks like this, I draw an affine section of the cone, the hyperbolicity cone, right? There's an origin out here, and you cone over this. That's the actual cone picture. And if you take a directional derivative, an interlacing polynomial, which will look something like this. And there's something out here. And so this is why these two univariate polynomials have interlacing roots. And now this, if you apply this Wronskian thing to these two polynomials, you get exactly this expression, because if you take a derivative with respect to t, you get the directional derivative with respect to the jth standard basis vector, which is the partial derivative with respect to xj. So if you apply this Wronskian idea to these two, you get exactly this one, which is why they are non-negative.
What happens if there are multiple roots? I mean,
you have to worry a little bit. But that's essentially where these polynomials come from.
But it's an honest Wronskian, right? It's the determinant of ff prime, gg prime. That's what you call Wronskian.
Yes.
Although Wronskian may have nothing to do with it, but it's still called Wronskian.
Yes.
No, it's first.
Okay. So this essentially proves one direction of the theorem. If the polynomial is stable, it's hyperbolic with respect to the positive orthant. So these polynomials over there are interlacing, and then you use the univariate case to show that they are non-negative polynomials. The other direction that 2 implies 1 is I will not comment on, but Petter will probably be happy to tell you more. And this, for instance, you can use as a stability test. You can go ahead, take your multi-affine polynomial, you compute them all, and try to prove that these are non-negative polynomials. And this was explicitly done in a particularly interesting example that we'll show up later. If you take the basis generating polynomial, the Varmus matroid, you can use this theorem to prove that it's a stable polynomial. Do we all remember what the basis generating polynomial is? Write it down. So the Varmus matroid is some matroid of rank 4 on 8 elements. Sometimes I think it's called V8. So the 8 elements, I will attempt a picture. So take, this is hard to draw. I will attempt. So what I'm trying to draw is not a 3 cube, but I want to draw the 2 faces that form a belt around the 3 cube. So you leave off 2 opposite faces. Say, I know, this one and this one, so you get, now it's probably impossible to see what I mean. So to specify the matroid, we have to pick 4 element subsets. Out of these 8, we pick all of them except for these 4 faces, and we pick one face, sort of a diagonal one, for instance this one. So we don't pick the 4 element subsets corresponding to this belt of 2 faces and one of the diagonal 4 element sets.
Those are the ones you don't pick.
These are the 5 ones I do not pick, and I pick all of the other 4 element subsets. That describes the Varmus matroid, and then these are the bases. And the basis generating polynomial is the sum over all bases of this matroid. The multilinear polynomial where you take the product I in B xi. That's a polynomial of degree 4 in 8 variables, and it's stable.
So here that you need to check whether univariate, not univariate, just polynomials.
You have to check all of these somehow, yes.
But for general hyperbolicity, you also reduce to checking whether polynomial is non-negative on let's say, actually positive. You need to check whether there are no real,
I will get to more refined statements along this line.
That was actually in one of my papers.
Yeah, I mean, I'm checking
not
such conditions.
General case.
I see.
So general hyperbolicity in homogeneous case can be reduced to stability, and stability.
Yes. Yeah.
Stability what?
So you given so I assume here problem is like you given E, or you're looking also for E.
No, I'm given E. Yeah.
So problem given E, you want to check whether polynomial is hyperbolic in direction E.
That's easy, right?
No, it's not easy. It's actually hard. Because it's happen equivalent to checking stability. And stability is essentially checking whether polynomial has real roots.
That's also easy.
Really? What are you talking about?
I will comment on more details.
The number of variables.
I understand. But
No, and it's easy when the number of variables is fixed.
check in one particular direction.
But you for all x.
Isn't that because you have a family of lines to check. And so in their paper, they actually show that all of these polynomials are not negative. They wrote down a sums of squares proof of this.
But there might be polynomials that are not negative but do not admit the sum of squares non-scientific. So it's not known whether stability would, that the polynomials that arise from a stable polynomial would have a sum of squares non-scientific.
Not always. I will also come to more details about
No,
that.
probably cannot because it's proven that it's a hard problem.
I see.
So in some cases, so checking stability is known to be hard.
Hard like NP hard? Or?
Yeah.
Ah.
What is that?
Hmm?
How was the proof?
I don't. It's actually reduced to the checking the non-negativity of polynomials.
Of the genetic.
But of special families, right? It's not clear to me, but I think we'll get
Yes.
more details and this discussion might be.
Problem. Given a polynomial, even I think quadratic, to check whether it's non-negative.
Lena, who did this? You did?
No, the stability, no, I did not do it.
No,
I did-
hardness.
No, hardness stability, I don't remember. I can get you. It's not me.
Okay.
So what I shown that you can go from hyperbolicity to stability. It's equivalent.
Doesn't it follow from Nemirovsky's reduction?
Not. Yeah, possible. Possible.
Right. Okay, and I asked you on the exercises to do some of these examples. So to attempt to check, to use this theorem to check for small matroids if the basis generating polynomials are stable or not, and you can. So if you want to do these exercises, this is a useful theorem to remember. Another thing that's quite natural, we already discussed, right? The definition. If you go back to the definition of being hyperbolic, you ask that all of the roots of a univariate polynomial are real. It's a parametric family of those, but so essentially you want maybe to know how do I count real roots of a polynomial. And we have seen some of the aspects of this problem in Jan's talk already, and I will review some of these things. And I've put here two references where you can find more information. One of the classical papers is by Krein and Naimark, originally in Russian. The English translation has this long title, and you can find it online. And there's a book by Bazou, Pollock, and Roy called Algorithms in Real Algebraic Geometry. They present all of these results also, and they do complexity analyses of these algorithms if you are interested in that sort of aspect. But the problem is very simple. You're given a polynomial in one variable t. Usually we assume that the leading coefficient is 1, so that it's actually degree d. And then we want to count. And there are several algorithms. We've seen the Hermite matrix before, and I will briefly review what this is. But there are other things you can attempt to do. There are Sturm sequences. It's an algorithm you produce from this polynomial, a sequence of polynomials, by essentially doing the Euclidean algorithm with respect to p and its derivative, and then you have to plug in points and look at sign changes. So that's roughly how Sturm sequences work. Resultants is also a technique that's very related to the Hermite matrix. Here also you produce some matrix out of the polynomial, and you have to check signatures and definiteness properties of this matrix. But I want to explain the Hermite matrix that we already saw, and we saw many of these other things appear. So for now, suppose I know the roots. Suppose it really has degree d, and I have the d complex roots in the plane. I compute the moments. I call these power sums usually. But so you fix the power, and then you sum over all of the powers of the roots. And then you build a matrix, which has Hankel form, by writing these moments sort of along the top row, and then the last column, and then you fill in the Hankel structure, and you have this Hermite matrix. So for me as an algebraist, right, if you don't really care about what the expressions are, it's kind of, there's a simple argument for why these moments must be expressible in terms of the coefficients of the polynomial, because this is, it's invariant under permutation, So it must be expressible in the elementary symmetric polynomials, which are exactly the coefficients. Okay, but then you would like to maybe do that also. You would like to compute what these expressions are, and there's these recurrences that enable you to compute them that we've seen before. I think they're called Newton identities. And here I've assumed AD to be 1, otherwise I have to divide here. And so, for instance, for a cubic, already this looks kind of complicated. So you start essentially with the degree here and one coefficient, all right. And so these, so let's see. So the ij entry has degree I plus j minus 2 as a polynomial in the coefficients. So this is the 3 entry has degree 4 in the coefficients of the polynomial. But you can write them down only in the coefficients, so you don't actually need to know the roots, of course, which would be sad if we needed to know the roots to count them. All right. Also, another aspect that's kind of annoying about these matrices, if you have a polynomial that is real-rooted, entries become quite big quite fast. So that's a thing that happens. Okay, but you can compute them. And the theorem says, which again is an exercise, that you can count the number of distinct complex roots by looking at the rank of this matrix. So in this example, that's a rank 3 matrix because we have 3 distinct complex roots. And the signature will tell you how many of these roots are real. So the signature of this matrix, which is the number of positive eigenvalues minus the number of negative eigenvalues of the matrix, counts the number of distinct real roots. So if you have a multiple root, it's only counted once.
I'm sorry, so the third row looks like it has 2 columns, is that right? 2 entries.
Up here?
No, the third row, the last row.
So this is supposed to be
1.
and this is the next.
Oh, up to here, okay.
Yes. So because of the Hankel structure, right? So these entries ought to be the same, and this entry is this one, and then here's maybe the spacing is non-optimal. But these are really just the recursions from the Newton identities. Secret. So let's try to use this to count real roots along lines. So to test hyperbolicity of a given polynomial. So suppose P has degree D, and I want to test with respect to a specific given direction. So I'm given E, and I want to know if it's hyperbolic with respect to E. If you also want to search for the direction, I don't even want to think about that problem. Okay, so what you're going to do is you want to test these univariate polynomials. So you expand as a polynomial in T. Because the polynomial was homogeneous, these coefficients will be polynomials in X that are homogeneous of sort of the right codegree. So this is homogeneous of degree D minus the degree of the monomial. So in particular, this here is a constant. This is just the value of P at E. And this here is a homogeneous polynomial of degree D. So now you've done that, you use these recurrences to plug them into the Hermite matrix. They are only in terms of the coefficient, which are now polynomials in X. Plug them in. So let's try this for this cubic polynomial in 3 variables. So that is hyperbolic with respect to this point. I've rigged the example. You expand. Here I only plug in x's now. That's the trick I used, that are in E-perp. Right? I choose a complement of the direction to reduce the number of parameters. I want to get rid of this x0, which is unnecessary. So this is really a problem in 2 variables. So I plug in 0, x1, x2. And then this is my direction. I expand as a polynomial in T. And now I plug these coefficients into the recurrences of the slide before. This is the degree. This here is minus this coefficient. This is a polynomial in this, and so on. And so you get this matrix, and you would like to know if this matrix is positive semi-definite for every value of x1 and x2. Okay. It's hard to test, but it's a possible way to test hyperbolicity in a given direction. So here's the theorem. That's really just applying the Hermite-Sylvester theorem to these parametric Hermite matrices. So how do you test such a thing? So one thing you can attempt to do is to use sums of square certificates for non-negativity. And there's the following observation. So this H of P is a symmetric matrix whose entries are polynomials. You can still make a quadratic form out of it in more variables. So I introduce new variables, y1 up to y equal to the size of the matrix, which is 2d minus 2, right? It's bounded by the degree of the polynomial p. And then I make this quadratic form out of it, but the coefficients of this quadratic form in the y's are polynomials in the x's. But the matrix A is positive semi-definite for every x if and only if this quadratic form is a non-negative polynomial in the x's and the y's. And that now you can attempt, now we have a polynomial, right? You can attempt to do this using semi-definite programming, for example. Write down a sums of squares proof of this. Sometimes this will work in the following sense. So if the matrix polynomial here is in one variable or homogeneous in two, as in our case of the slide before. If it's homogeneous in two, then you can get rid of one of them. So if this is in one variable, then every non-negative symmetric matrix polynomial is a sum of squares. There exists such a certificate for the non-negativity of this matrix, which doesn't tell you how hard it is to find, but at least it exists. So in this sense, turns out if you do the details, that for homogeneous polynomials in three variables, that's an exact method. But that reduces to the problem of finding the sums of squares certificate. In more variables than three, this is a relaxation approach. As usual, you can't guarantee, even if it is non-negative, that you will find such a proof. All right. So this has essentially been done explicitly and more cleverly in a paper by Raghavendra, Ryder, and Nikhil. It's essentially this method I've just discussed for homogeneous polynomials in three variables or stable polynomials in two, which is how they phrase this. So there is an algorithm that checks whether our parametric Hermite matrix is positive semi-definite for every axis in a running time that's polynomial in the degree of the polynomial we are given. And I want to sort of roughly describe what the things are that make this, so what the clever aspects are. How do you check this? They don't use sums of squares because we don't know the complexity of sums of squares of STP feasibility problems. So you have to do something else. So let's try to see roughly what you can attempt to do in this case.
Excuse me.
Yes.
If you do just Tarski, so it would be worse complexity?
Which is really bad, yeah.
Huh?
Yeah, I mean,
But
sure.
it will be polynomial.
Quantify elimination.
I will not be 5.
Yeah. Quantify elimination because here the number of variables is small.
Sure, but even then.
But it will be polynomial in D.
He's right.
Yeah, it'll be
For fixed number of variables, yeah.
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 Sure.
Yeah, but so it won't be D to the power 5, so this is the point, yes?
I haven't checked. Do you know off the top
It'll
of your
be
head?
some polynomial. I don't know what it'll be.
Okay.
I mean,
Don't
yeah.
know what the exponent is.
2 to the 2 to the 2 5 times.
Okay, yeah. Okay, let's not. That's pretty big.
No,
No, you do regular.
regular.
So we're trying to check. So first of all, this is phrased for stable polynomials, right? So I want to get back to my Hermite matrix. So you have to carefully homogenize. And this was done, so sort of step one is a careful analysis of how you have to homogenize such a thing, which was done by Freie and Freie. So let's see. So a polynomial, which is now not homogeneous, but in two variables, is stable. If and only if the following polynomial is hyperbolic in some direction. So you homogenize the thing. PH is now a polynomial in 3 variables. And you get it by, suppose the degree is d. So you plug in x divided by z, y divided by z into this 2-variable polynomial, and then you clear denominators. So you get some homogeneous polynomial in x, y, z. So if this homogeneous thing is hyperbolic, in directions with respect to all E in R2 cross. So you can plug, so E1, E2, E3, E1 and E2 can be, should be positive orthant. It's a 2-dimensional positive orthant where you have the last coordinate equal to 0. So that is how you prove that. That's not very hard to see. You have to sort of carefully homogenize and check. So, but now you have to sort of test hyperbolicity of this polynomial with respect to this family of directions, even. So that's step 2. I need something like this. So let's try to check. Claim. This implies that P is stable. If and only if, now come the conditions we want to check. 2 things are satisfied. Condition 1, there's a 1-parameter family of things. Polynomials Q, gamma of T, which you get by plugging in gamma plus T, comma 0. No. P is in comma 1 if I want, well. Anyway, you plug in this thing into the bivariate, original polynomial. If this is real rooted in T, and secondly, you need to check that the hyperbolicity cone is big enough, so you have to check that the homogenization along sort of a spanning line segment, this is a compact base of this cone, is positive. T between open, right? 0 and 1. So this is essentially checking that it's hyperbolic with respect to all of these directions. Because I've taken, if I know that it's hyperbolic in one special direction, and I know that it doesn't have any zeros along this line segment, I know that the hyperbolicity cone, because it's convex and a cone, contains the positive orthant. So really checking for zeros along this line segment checks that the hyperbolicity cone is what it ought to be. And this is sort of the parametric Hermite matrix part. This is the real rooted business you need to check. All right, now you have to do this. So what do? You compute the Hermite matrices, and the moment formulas went away. So these coefficients of this polynomial in T are now polynomial expressions in gamma. You know the degrees. By these recurrence formulas, you can bound the degrees of the entries of this parametric Hermite matrix. So if you compute the characteristic polynomial of this parametric matrix, you can bound the degrees of the so the coefficients of the characteristic polynomial will also be polynomials in this parameter, and you can bound the degree by staring at this carefully enough. So what they attempt to do is compute the characteristic polynomial directly by interpolation, because you have bound degree. So you compute these Hermite matrices, you evaluate them at roots of unity, because that works well, and then you compute the determinant, then you have values of the characteristic polynomial, and then you interpolate to determine these polynomial coefficients. Okay, so that's a lot of work and standard technique, I think. So what have you gained? Once you have the coefficient of the characteristic polynomial, you can check if the matrix is PSD by checking that the coefficients are non-negative polynomials. So you produce a bunch of univariate polynomials, and you have to check that all of them are PSD. That's essentially one way you can attempt to do this. And I think you get a worse bound for this, right? Sort of, you have to be even more careful. You want d to the 5. You don't compute these. No. And then you have to be even more clever and not compute the whole characteristic polynomial, but sub-resultants or something. And then you get it a little bit better, but you have to be even more careful. But so for these small number of variables, you can do this. And in general, I think it's not so clear what you would attempt to do. All right. Of course, I haven't told you how you check non-negativity of a univariate polynomial. Even if you want to do this algorithmically, you have to be careful how to. Okay. Another thing you can maybe attempt to exploit is what the set of all hyperbolic polynomials looks like in this vector space. Fixed hyperbolic polynomials. We have fixed the number of variables. We look at homogeneous polynomials of some degree. And we have a fixed direction. Then there is a set of hyperbolic polynomials with respect to this fixed direction. And the geometry of the set, or the topology, I should say, was studied. So I never pronounced this name. Does anyone know Dutch? I have no idea. There are various. Some people call this now, others newage. I don't know. Anyway. So he wrote a note on hyperbolic polynomials back in the 60s, maybe even. And to understand what the theorem says, we need sort of one more property. A polynomial is even better than hyperbolic. It's strictly hyperbolic if it does not have multiple roots along any of these lines. So whenever you restrict to these lines, you get a univariate polynomial. None of them have any multiple roots. It is equivalent to a geometric property. So if you draw the hypersurface, if you draw the zero set, you draw this somewhere, it's equivalent to the fact that the zero set does not have any real singularities. You can only have a multiple root if, for example, some of these connected components come together. So if instead of this, you have a picture like this. And along this line, here, we'll have a multiple root. And that's essentially the only way this can happen. That's a lemma to prove. So strictly hyperbolic is equivalent to the fact that the real zero set is smooth. The gradient is non-zero at every real zero of the polynomial. And these are special. So in order to state this correctly as a technical detail, you have to normalize everything. So I'm only looking at hyperbolic polynomials that evaluate to 1 at the fixed point. Otherwise, some of the statements do not mean what they should. And then now I have two sets. I have those polynomials that are hyperbolic in this direction, and I have the subset of those that are strictly hyperbolic. And then the following things are true. The set of all strictly hyperbolic polynomials is an open subset. If you believe this characterization, that's kind of plausible, right? Having a singularity is a closed property. And if you don't have one and you wiggle the coefficients, roots vary continuously, it should stay. Roots should stay simple along these lines. So that's essentially the reason behind this statement. And you can approximate every hyperbolic polynomial by strictly hyperbolic polynomials. This is exactly the closure in the Euclidean topology of the strictly hyperbolic ones. And the interesting part that may be useful is that this is actually contractible. So homotopy equivalent to a point. So there is you can connect every hyperbolic polynomial by a path to a strictly hyperbolic polynomial, and the path sort of works simultaneously for all of them. That's what the homotopy equivalent is. Sort of use the same path, and you'll see it on the next slide, to connect any hyperbolic polynomial to some mysterious strictly hyperbolic polynomial that sits in there. And this mysterious path looks kind of ugly, and this is the definition. I'll walk you through in a second, but it really is a very, very simple idea, and the very simple idea is, again, you should look at univariate, the univariate case, what happens along one line, and then generalize this correctly to the multivariate case. And the univariate lemma is one of the exercises. Which one? Exercise 9. It's a very simple observation. If you have a univariate polynomial and it's real rooted, then let's see, p plus s times p prime is real rooted for every s. It's essentially this s that shows up here. And you reduce the multiplicity of a root if you do this. P plus s times p has simple roots everywhere. Every root that is not a root of p simple. And the multiplicity, of course, of a root of p, if it has a multiple root, the multiplicity goes down if you do this with an s that's not 0. And that's really what is behind these mysterious things on this slide. Really, sort of, you know how to do it along one line. You need to think carefully of how you do this sort of for all lines simultaneously. And the trick is that you look at these weird operators which take partial derivatives with respect to t. So I've made some simplifying assumptions. So my direction is the first coordinate vector. And I call the first variable something special, namely t, and all of the others x's. So this is, if you want, more generally, this is the directional derivative in the hyperbolicity direction, which I've now normalized to be the partial derivative with respect to the first vector. And then you have this perturbing parameter s, that's the s from the exercise. And then you have to make this homogeneous again, because we want to talk about hyperbolic polynomials, so you have to pick some linear form to fix the degree of this thing. And which linear form you pick is up to you. And sort of these operators that show up here tell you, well, why not pick all of the variables? This is sort of to take care of the fact that you need to check this along all of the lines. So if one of the xi were equal to 0 in your line, then maybe this thing would not exactly correspond to our univariate lemma. So you sort of do it just to be safe in all directions, or in all of the directions of a basis. And then you're fine. So that's essentially what smoothes out into a strictly hyperbolic polynomial. But we want to connect to a fixed one, right? We want this to be a contraction, and that's why you do this weird gs. You rescale the x's, because for s equals 0, this is always the same polynomial, no matter what p was. But it's a hyperbolicity, it's a stability preserver. So for s equals 0, no matter what p was, this is always t to the degree. And then you can sort of apply all of these things, you get something, but that does not depend on the actual p anymore. That's sort of the point that all of these paths connect to. These f1 apply to t to the d. That's the mysterious strictly hyperbolic polynomial that sits inside where all of these paths connect. And these are paths as a function of s, right? That's the parameter I move from 1 to 0. S is 1, then I don't do anything because I don't rescale here, and here I've done a 1 minus, so s is 0, so I don't do anything with these maps either. So for s equals 1, I just get my p back. So this is a very explicit path.
You start at s equals 1 and go down to 0. That's the
Yes. I mean, it's a homotopy equivalence. Exactly. So these things look kind of complicated. If you want to know what happens, do exercise 9, and then you've understood the essential part of the argument. The rest is worrying about parametric families of lines in the correct way. So of course, not clear how to really use this. One thing you can attempt to do is try to determine now you fix your polynomial p. Now you have this path as a parameter, is a univariate thing as a function of s. So you can try to detect if somehow along this way the polynomial is not strictly hyperbolic anymore by looking at something like a discriminant or something. Because the boundary of hyperbolic polynomials by the theorem on the slide before is really determined by those that have a real singularity. So if you perturb this a little bit, you can make it non-hyperbolic. But in order to be able to do this, the strictly hyperbolic polynomials are open. You need a singularity. If you perturb a strictly hyperbolic one, then it will remain a hyperbolic polynomial with respect to your fixed direction. So you can attempt some things like this, which I think computationally are very non-promising because these discriminants are notoriously very difficult to compute. Oh yeah, yes. So that's the path that proves the theorem on the previous. So instead of doing these discriminant things, a natural thing you can try from an algebraic point of view, which complexity-wise is also, I think, maybe not the best approach, but you can at least do some small examples, small degrees, quite explicitly, is to look at a resultant type of thing. So what's a resultant? The resultant takes two polynomials as input, and it produces a polynomial in the coefficients that is 0 if and only if they have a common root. So you can try to use this on a real and imaginary part of your polynomial in the following sense. So suppose you have p, hyperbolic with respect to the first standard basis vector. So you want to test, in fact, if all of these univariate polynomials as a parametric family in X is real-rooted. So instead of doing this, maybe you plug in sort of a general complex number. So now T1 and T2 are constrained to be real numbers. Before here, T is a complex, you plug in a complex number here. Now I want to plug it in like this with its fixed real part, which is now a real variable, and its imaginary part, which is now a real variable. Okay? And you multiply this out, you get some things that have an I in front, some that don't, and this you call the real part of this polynomial, and an imaginary part. And now the question is, do they have a common root? So a polynomial is hyperbolic in this direction if and only if they have no common root, where the imaginary part is non-zero. Right? I want this to be real-rooted, so I want the imaginary parts of every root to be 0. And now I phrase this in a sort of contrapositive resultant type way. Okay? So now I want to check if these polynomials have no common real roots, where the imaginary part of my complex number is non-zero. And this you can check with resultants, or more generally, right? So now you want to check if two polynomials, in fact, have no common real root. And there's a tool to do that. It's called the real Nullstellensatz, which gives you a certificate of infeasibility for this type of systems of polynomial equations. So what it says is if you're given real polynomials that do not have a common root, which is exactly what we want, then there exists a certificate of this type. So there exist polynomials, any polynomials q1 up to qk, and a sum of squares of polynomials such that this holds. So why is this a reasonable certificate of infeasibility? If you plugged in a common real root, this term would go away, right? Because all of the fj's would be 0. It's a common real root. On the right, you have -1, and on the left, you have a sum of squares evaluated at a real point. It gives you a non-negative number. That's a contradiction, so this is really a certificate. If you can write this down, there's an immediate proof that there's no common real root, just by plugging it in. Now, of course, we have this constraint that S2 is non-zero and in a not equal constraint, which you can get rid of with a standard trick. So you introduce one new variable for these non-equal constraints, and you apply the real Nullstellensatz to the polynomial real part, imaginary part, And then you enforce the condition that T2 is non-zero by having that this polynomial is equal to 0. So that's the standard trick. Introduce one new variable, and then I just wrote down really this certificate for these three polynomials. So the inequality, this inequality constraint gives you here a new variable and a new equation. All right. Any questions so far?
Yes. Is there like any natural analog of that strict hyperbolicity for stability?
I'm not sure. Yes?
No,
Strictly
because
stable?
I had one. I'm just curious. Maybe it's appeared in this context.
I know. I don't. What is your general
I have one too.
So maybe you can
Mine is
discuss.
when at least there are no roots where all real parts are non-negative and at least one is positive. So it is like yours,
You can do it differently. You can.
but it's equivalent to this one. I actually call it SS stable.
I think you can do it in several different ways. You
But
can
it's
do it-
equivalent
you can do
to-
it-
yes.
You can do it via the hyperbolic polynomials, or you can do it by sort of finding there's a way of, if you have complex coefficients, there's a natural way to define it too.
But is it equivalent to what I said, let's say in a real, let's say
So what did you
real,
say?
so my definition would be like this: real homogeneous case, and there are no roots where with all real parts non-negative and at least one of them is positive. So the standard stability, there are no roots with all
Yeah.
real parts. Is it the same?
I don't know.
Okay. Because for that, and also this, was it ever used, this Nietzsche result, or for some proofs? Was it, or it just stands on its own? That result about the path, the topology.
It is convenient that you can assume strictly hyperbolic. That, I mean, this part, for example, is used. You can approximate every hyperbolic polynomial by a strictly hyperbolic one. I don't know if this path explicitly has been explicitly.
Kind of important part in the proof, important trick. That you want to prove something, and you use this result for.
Excuse me, for this method?
No, for that, for that approximation by strictly hyperbolic.
I'm not sure off the top of my head what the answer is. Some of these topological things. I mean, it's a convenient, this closure thing is a convenient thing for Helton-Winikoff theory.
I mean, you could imagine the results about these hyperbolicity going to strictly hyperbolic polynomials, like being whatever projections of.
Yeah.
You could imagine using this to say, well, you can approximate.
This approximation thing is used, yeah, that for sure. But the path explicitly, I'm not sure if ever this path.
I'm asking because that analog of that stability, that strict stability, it actually makes certain induction easier than with stability.
Yeah, probably. I just don't know an example, but it has probably been used.
I mean, a strict hyperbolicity makes this question of finding a spectrohedral or whatever spectrohedral shadow easy, right?
There's a non-constructive proof for the existence of these things in that case. All right. So this is sort of the hyperbolicity testing part. So I think it's time for some exercises. As you may have noticed, the exercise sheet is very long. So pick some problems to work on for now. Some of them have shown up in earlier talks. Some of them are more computational. Some of them are more theoretical. Some of them you can't actually really solve if you don't know the things and haven't been to my second talk yet. So we'll look at some of the problems after the second talk. And what I would like to try today, what I would like you to do is to take the time sort of until the second talk, the coffee break and the exercise part to work on these problems. Optimally, you would get together with someone you don't know yet, especially from a different department. So who's in the CS department? All math people, look carefully. All math people, who's in the math department? I'm in the math department. So all CS people, look carefully and try to maybe find someone to work on these problems with. And then if you're interested in solutions, first of all, I'll be around. You can ask me questions. And in the lunch break, I'll grab a sandwich or something, and I'll be upstairs on the second floor. So we can, if you want to present or ask questions or talk about something, everyone who wants to do such a thing, we can meet sort of for lunch on the second floor. And then discuss all of your questions, solutions, problems, approaches, and so on. But for now, I would like you to use the time to actually do as many of them as you feel like or can. Whatever. And then I guess we'll be here again at some point. 11:15-ish.
Oh no, what?
For the second talk.
You
Yes.
don't want to have a...
We'll do it over lunch.